I will talk about Titin too. I think my presentation will fit nicely after the amazing Anthony presentation. So let me give you another brief introduction about this amazing protein that spans the whole of sarcomere, connecting the Z line to the tip of the myosin filament, and then associated with it, run up to the middle of the sarcomere in the M line. In the A band, Titin takes periodic interaction with myosin motors from the third layer of the myosin crown in the P zone to the tip of the myosin filament, while in the I band, Titin is composed by these three different segments, of which only the first two, the proximal, poly G, and the PAVK segment, account for Titin extensibility. In this region, Titin is able to transmit stress even when there's no myosin motor attached, and it's responsible for the passive force developed when a muscle cell is stretched at rest. But the Titin passive stiffness at physiological sarcomere length, so here between 2.2 and 2.7 of the first sarcomere length passive relation in frog, we will get there in a minute. This Titin stiffness is too low to account for a role of Titin as an efficient mechanical link between the Z line and the myosin filament, able to sustain a mechanosensing-based activation or to prevent inhomogeneity among the sarcomere during activation. So the aim of this research is to investigate the role of Titin during contraction in situ, so in a single intact muscle cell of rana esculenta. The frog skeletal muscle is our sample of choice because it allows us to perform a high resolution of sarcomere mechanics and therefore to record change in force by the order of piconewton per active filament and change in length by the order of nanometer per half sarcomere. The problem is that a quantitative description of Titin in situ in the half sarcomere is hampered by the presence of the array of myosin motor in parallel with it. So in order to overcome this problem, all of our experiments are conducted in the presence of 20 micromolar paranitroplebistatin in order to inhibit actin-myosin interaction. So we have preliminary experiments that have shown that in the presence of 20 micromolar paranitroplebistatin, both the ATPase activity of frog HMM and the fiber force during tetanic stimulation are reduced to zero. Here in a figure in blue, we have the force developed in normal Ringer solution, while in orange, we have the development of force in the presence of paranitroplebistatin in response to a tetanic stimulation. So it's true that paranitroplebistatin reduced to zero the force during stimulation. But the structural evidence of the action of the paranitroplebistatin at the level of the myosin motors was obtained by collecting 2D X-ray diffraction patterns at the EDO2 beamline of the European Synchrotron Radiation Facility of SRF at Grenoble in France. And so the effect of paranitroplebistatin on the X-ray signal marking the structural states of the thick filament, such as the equatorial reflection, the first myosin base layer line reflection, and the meridional reflections, was determined by comparing patterns collected in a normal Ringer solution. Here in the superimposed intensity profile, there are the black one in normal Ringer solution at rest, and the blue one in Ringer solution, but during tetanic stimulation, compared with those obtained in the presence of paranitroplebistatin. And as you can see, in paranitroplebistatin solution, even upon tetanic stimulation, all the parameters maintain the value characteristic of the resting state. So with this proof in mind, we determine the mechanical properties of titin at different sarcomer lengths, both at rest and during tetanic stimulation, by imposing 100 microseconds for step, with amplitude ranging from 12 to 40% the isometric tetanic force in control. And through the analysis of the lengthening parameters, such as L2, the lengthening attained at the end of this phase 2, obtained by back extrapolating at the half time of the step, the tangent to the third phase of the transient, or the velocity in this third phase, V3, given us by the slope of the tangent, we discover some amazing half sarcomer behavior. In fact, at rest, the amplitude of the first component of the lengthening transient decrease at larger sarcomer length. In the dark color, you have the resting lengthening transient. And for small sarcomer lengths, such as 2.5 micrometer, the lengthening attained is so big that saturate the range of movement of the motor, but became smaller at 2.7 and even smaller at 3 micrometer. So we have a half sarcomer that is quite extensible, but becomes progressively steeper with the increase in sarcomer length. On the other hand, in the active fiber, represented here by this light color, the first component of the transient is much smaller and briefer than at rest, but mostly important, is completely independent by the sarcomer length. So our first conclusion is that the increase in effective sarcomer stiffness upon activation indicate that the iodine titin switch from an off state characterized by a large sarcomer length dependent extensibility to an on state characterized by a high sarcomer length independent stiffness. Both the resting and the active mechanical properties of the sarcomer in the presence of paranitoblebistatin are summarized by this equivalent mechanical model. And so the larger sarcomer extensibility exhibited by the resting fiber is explained by the entropic contribution of the, I'm sorry, the fan of my computer is going wild. Can you hear me well? I hope so. Okay, I see Anthony. Okay, okay. The larger sarcomer extensibility exhibited by the resting fiber is explained by the entropic contribution of the randomly orientated element joining the immunoglobulin in the proximal poly-G segment, represented here by the magenta box. Their number at full overlap is maximum. The number of these elements that a full overlap contribute to the half sarcomer extensibility is maximum at full overlap, but progressively reduce with the increase of the sarcomer length and become zero at sarcomer length 3.1 micrometer, at which we have reached the contour length of the proximal poly-G segment. In the active fiber, in the same range of sarcomer length, the extensibility of the extensibility is constant and quite small, and a sensible explanation for that is the activation-dependent formation of a link in a point in titin distal to the proximal poly-G segment with a nearby actin filament. In this way, the extensibility of the poly-G segment is completely eliminated by the in parallel addition of the much steeper actin filament. And then that explains the increase in sarcomer stiffness during the activation. Now, whether this active stiffness increase in titin in response to an increasing load imply a resistance to a muscle shortening is tested by recording the response to a stepwise drop in force, so to a negative force step this time, imposed on the active fiber at 3 micrometer circular length, at which the steady passive force is enough to make this measurement feasible. And apart from the response to a smallest negative force step that maintains the multi-phase aspect of the lengthening transient in response to a positive step, the shortening transient is characterized by a monotonic high velocity that increase abruptly with the increase in the size of the force step, up to a values of 1,000 of nanometer per second. And so we are now able to build a velocity force relation, both for lengthening and for shortening. And the different slope of this relation, meaning that the resistance opposed by Titin during the lengthening is 3 orders of magnitude larger than the resistance opposed during the shortening. 3 orders of magnitude because 2 orders is given us by the scale and 1 additional order is given us by the different slope. Okay, but another very amazing aspect is that through the analysis of this negative first step, the response to a negative first step, we know that the recoil of Titin does not limit the maximum shortening velocity in control condition. In fact, the restoring force exerted by Titin at 3 micrometer is about 25 piconewton. Is this arrow here, and account for a velocity that is more than twice the allowed and shortening velocity of the myosin motor in control condition. So we can conclude that in the active fiber, the high-band Titin acquire rectifier properties, opposing a high resistance to stretch, but allowing free shortening. At this point, we were very interested in this on state of Titin as a mechanical link between the Z line and the myosin filament. And so whether and how this on state of Titin has a role in the mechanosensing based activation of myosin filament was investigated using small angle X-ray diffraction. And so here we use 3 millisecond X-ray time window exposure to record the structural change following a 50 piconewton per step imposed on the stimulated fiber at 2.6 micrometer, always in the presence of paranitroplebistatin. In order to have a time course of the structural change, the first time window exposure was placed 5 milliseconds before the step, and then 3, 10, 20, and 30 milliseconds after the step. And the first change, the first results that we have is that the change in the X-ray signal following the first step imposed on the stimulated fiber show a hierarchical organization of the structural change in the myosin filament. In fact, the earliest change is the increase in the spacing of the third, and the 6th meridional reflection, simultaneous with the decrease of the intensity of the forbidden reflection. All this change occurs without any significant change in the intensity of the M3 reflection. And so now I know that everybody knows at this point, but I would like to remind you that the M3 reflection emerged from the axial periodicity of the myosin head on the thick filament, while the M6 reflection reports more specifically the extension of the thick filament because it originated on a periodic structure on the backbone of the filament. And typically, the drop of the intensity of the forbidden reflection is associated with the loss of the triplet perturbation of the myosin head, explained with the loss of interaction of the N-terminus of the myosin binding protein C with actin due to the reduction of the overlap of the filament. And so this loss of perturbation the loss of the triplet perturbation is synchronous with the structural transition leading to the extension of the filament that is also marked by the increasing spacing of the M3 and M6 reflections. So yes, we have increase in the extension of the thick filament, but we don't have any change apart from minor decrease in the intensity of the M3 reflection after 30 milliseconds, meaning that we have filament extension, but we don't have the loss of the off state of the myosin motors. And then with a slower time course in response to a first step, we have a decrease of the intensity of the first myosin base layer line that emerged from the three-stranded helical packing of the motor. And in the opposite direction of this decrease in the intensity, we have an increase in intensity of the equatorial reflection 1,1 from the lattice plane containing both thick and thin filament, but without any loss without any change in the intensity of the equatorial 1,0 reflection, meaning that we have an increase in the mass aligned with the 1,1 lattice planes, presumably constituted by the myosin motor, but we don't have any loss of mass in the 1,0 lattice plane. That is important. But another important piece of information is given us by the fact that with the increase of the spacing of the M3 reflection, we have a change in the fine structure of the M3 reflection. Specifically, we have an increase of the intensity of the low angle sub-peak among the wall intensity of the reflection, represented by this parameter LM3, and a decrease of the intensity of the high angle peak above the wall intensity of the reflection. Now, why this is important? This is important because if the increase in extension of the thick filament following the first step produce an increase in the axial periodicity of the motor and an increase in the interference distance between the two myosin motor arrays by the same amount, I shouldn't have any change in the fine structure of the M3 reflection. So this means that the extension of the filament is not homogeneous. So we simulated a simulation from the LM3 and HM3 spacing relation is built, and in which different extent of the thick filament are assumed to contribute to the increase in spacing, with the n equal 1 represent the first layer near the bare zone, n equal to the second one, and so on. And the results of this simulation is that the increase in the axial periodicity of the myosin head induced by the first step doesn't concern the central region of the thick filament. And with central region, I mean obviously the bare zone, but even the first 2 or 3 layers nearing it. So apparently, the stress-dependent myosin filament extension is limited to the region in which the A-band titin takes periodic interaction with the myosin motors. And so a mechanism able to explain the relation between all of these signals is based on the hypothesis that at rest, the 6-titin filament associated with the half-thick filament, the magenta dot here, share the same 6-fold rotational symmetry as the actin filament, the yellow dot. So they share the same lattice plane, while the myosin motor emerged from the backbone of the thick filament with a 9-fold screw symmetry. But in the actin fiber, the step induced the change in opposite direction of the intensity of the first myosin base layer line and the equatorial 1-1 reflection without change in the intensity of the 1-0 reflection, indicated that the stress transmitted to the thick filament via the stiffness I-band titin displaced the motors towards the 6-fold rotational symmetry of the actin filament in a load-dependent manner. So the extension of the myosin filament is followed by an azimuthal movement of the myosin motors towards the lattice plane containing the actin filament. So I have a summary of all the results of this talk. So we have the change in sarcomer stiffness upon activation that indicate the switch of the titin from an on state characterized by a large sarcomer length-dependent extensibility to a non-state characterized by a high sarcomer length-independent stiffness, that in the active fiber that I-band titin acquire rectifier properties opposing high resistance to stretch but allowing free shortening, that the change in X-ray signal following the first step imposed on the stimulated fiber show a hierarchical organization of the structural changes in the myosin filament, that the stress-dependent myosin filament extension is limited to the region in which I-band titin takes periodic interaction with the myosin motor, and then that the extension of the myosin filament is followed by an azimuthal movement of myosin motors toward the lattice plane containing the actin filament. All of these results can be summarized in one big take-home message here, and is that in the active fiber, the increasing stiffness of the I-band titin is able to transmit even at physiological sarcomer length, a change in load to the thick filament, causing a displacement of the myosin motors that represent the preliminary step toward myosin-actin interaction. With that, I finish. I would like to thank all the Physiolab, all the people involved in this work, and then Narayan from the help at the synchrotron. He's the responsible of the EDO2 beamline, and Andras Malnaz-Victimadia for providing us the blebistatina. Ma, of course, for the invitation today. I'm very glad to be here, and all of you for your attention.
Thank you for the nice talk. Okay, if anyone has questions, you can unmute yourself and ask the question to the speaker.
I think these last couple of talks have been really great. Some of the things that I'm thinking about with you guys saying as you're stretching the sarcomere, and maybe there's even some heterogeneity in structure from the M band towards the Z line of the thick filament, do you think there's some of the changes in the morphology or the tapering of the D zone or the distal portion of the M line that might be exacerbating or extending or coordinating some of these heterogeneous changes and stress and strain as you're pulling on the filaments?
Among the thick filament.
On the thick filament, yeah. Because I hadn't thought much until last talk with Anthony, putting the tapering of the D zone. I mean, I've thought a lot about how stress and strain and coordination of the mechanics of the filament might affect how cross bridges bind and how stress propagates throughout the sarcomere, but I haven't ever considered what might be going on with, if you look back that Lori Nyland's paper quite a while ago suggested that the myosin binding protein C adds stiffness to the C zone, or the C zones are stiffer than the rest of the filament. And then Anthony was talking about the tapering. There might be like quite a bit more details that are more complex than we've been modeling or we've been thinking about. And Kate, what you were just saying with the heterogeneity of how stretch might not be uniform, I mean, it
Yeah.
all points to something that's a little more complicated than we've been assuming. Is I guess, I don't know if that's a question or a comment or a point of discussion, but these
Yeah,
have been
it's a very
really interesting couple
interesting
talks.
comment, because there also the new work of Padron and Craig and Dutta, of which Anthony just talked in the previous talk, that show that maybe the thing is very complex and is a collaboration of the 3 myosin head with the Titin and with mine binding protein C. So it's clear that the level of complex here is much higher than what we expect. But I think for my part, what I can see is that the Titin surely have a role in this. But I think that with the simulation and the new work, the things that, sorry. I think that the thing is more complex than that, and that not only Titin collaborating in that. So maybe there is a role of this inhomogeneous density of the thick filament in the C zone in respect to the P zone and the D zone and so on. But surely Titin has a great role in all of that. Yeah.
I have a comment or question that actually piggybacks off of this. So when you talk about the D zone tapering, 100%, right? So at the beginning of the D zone by the C zone, stiffness is the max, right? Because we have 33 tails packed there. As we move to the tip, the stiffness of the region is the same, but there's less mass there, right? So if the same force is applied all the way through, you're going to get bigger stretches at the tips of the D zone than by the C zone. And I mean, we're talking about going from 33 tails squished together with myosin binding protein C and stuff to just 3 tails and the heads, right? And Titans, which are practically the same size at that point, which is pretty crazy. I think that one thing that your group can do with the modeling that you do is actually like you can mechanically identify how much things would stretch with a simple model, and then you can drop that into your guys' prediction models about what's going to happen with the diffraction patterns. I think that'd be super interesting, really relevant for this field.
Does anybody know where Titin actually, I mean, I know this has been discussed a lot and there's drawings that show a lot of different things, but where does Titin actually leave the thick filament? Because that would change how things stretch in the D zone as it's starting to taper. Does anybody actually know, or do we know? I know there's like words that maybe calcium affects where it binds and leaves, and
Yeah, go Anthony, you know it.
Okay, yeah, sorry, Titan person. Yeah, so the 6 Titans run on the thick filaments.
Yeah.
And they merge into all 6 Titans meet at the tip of the D zone, and they create
in
this
the
nice
polymer. In the distal poly G segment too, they associated the 6 molecule of Titin.
And it seems
so
to be
just
pretty
to
tight.
be clear, they actually run all the way to the very end,
and then continue another 100 nanometers by themselves before they split off to go to the individual thin filaments. We can talk about this offline for sure.
Well, I can comment on it. Well, structure and elasticity should be matched. So we really need to create models which are more detailed, especially with these new structures. And one also important point is when you merge one element with the other one, so is that whole force transferred at the short region or longer region and such kind of things. This depends on interactions, how these interactions are. And this also can create homogeneity. And one also important is that in C zone, we have much more proteins on there, which contribute to stiffness, myosin binding protein C, Titin, and others. So these are all elements, but they should be put together. And as more we know about structure, this will be easier to understand. And then we can interpret data better. But at this point, probably we don't have that clue yet. But it's good. We have new questions, so new research should be done there. Thank you.
Okay, if no more questions, we'll move on to next speaker. And you have more questions, we can ask during the breakout, or you can just talk offline.